This module is on the famous Bolzano-Weierstrass theorem, which is one of the most important theorems in all of analysis. So please grab a cup of coffee and be up to your optimum concentration levels. We are going to give two different proofs of this Bolzano-Weierstrass theorem. This theorem states that any bounded sequence must have a convergent subsequence. Convergent sequences are bounded, we have already seen that, but the converse is not true, it's only partially true. We are going to provide two different proofs of this result. The first proof relies on an ingenious observation by Donald Newman in 1953. This theorem is around 100 years older than that. But nevertheless, this observation was made only very recently, relatively speaking. So that states the following. Lemma, this is due to Newman. This states that let An be a sequence. An be a sequence. We can find a subsequence that is increasing or a subsequence that is decreasing. So any sequence, no matter how complicated and bizarre it is, will either have a will either have an increasing subsequence or a decreasing subsequence, or most probably both. Okay. Now, first we will make a simplification. It's going to be a proof by cases where I'm going to leave one of the cases to you. Okay. Either An is greater than or equal to 0 for infinitely many choices of n, or An is less than 0 for infinitely many choices of n. In all likelihood, both might happen as well. Okay, it is possible that a sequence has infinitely many positive terms and infinitely many negative terms. Okay, but the catch is at least one of these properties must hold. We will prove only the case when An is greater than or equal to 0 for infinitely many choices of n, for infinitely many n. The other case is exactly similar, and I am going to leave that to you. In other words, we can make the assumption, we may assume that xn is a sequence, not xn, sorry. We may assume that An is a sequence such that An is greater than or equal to 0 for all n in n. What have I done here? Well, again, remember what we are trying to prove. We are given some arbitrary sequence An. We don't know its behavior. It could be the case that infinitely many terms are positive or infinitely many terms are negative. Something, one of these definitely has to happen. I am going to prove it only for those sequences that have An greater than or equal to 0 for all n in n. Why am I done if I do it only for these sequences? Well, look at the original sequence An we started out with. We have first made the assumption that An is greater than or equal to 0 for infinitely many n. In other words, we can find a subsequence of An such that all terms in that subsequence are greater than or equal to 0. What I have essentially done is I have removed this subsequence from the original sequence An and created a new sequence, and by abuse of notation call this new subsequence also as An, and I am going to prove the result only for this An. Okay, so essentially what I have done is I have extracted a subsequence re-index that subsequence, and I'm going to consider only that subsequence. So please contemplate for a few minutes after pausing the video why, if you show only for this case, we are done. Why we can make this assumption. Okay, it's not hard, it's just basic logic. Okay. Now we have made the assumption that an is a sequence such that an is greater than 0 for all n. We are going to show that this sequence must either have a subsequence that is increasing or subsequence that is decreasing. Okay. Now what we are going to do is we are going to imagine that the sequence is plotted as a graph. Okay. So imagine we have 1, 2, 3, 4, 5 and so on. Okay. And imagine you're plotting the sequence. So this might be A1. I'm plotting it as a stick, of course. This might be A2. This might be A3. This might be A4. This might be A5. Then so on and so forth. Let me draw a few more terms for representation. Okay. Now imagine that you have these sticks laid out in front of you and you climb to the top of one stick and you're standing here on this stick. Okay. Don't ask me how you are able to stand on an infinitely small stick. This is just for illustrative purposes. Now imagine that you are standing on top of one of these sticks and you look to your right. Okay. What can happen? Well, there are two possibilities. Either every stick to your right is smaller or at the max as large as the stick you are standing on, or this isn't the case, right? So assume for the time being that you are standing on a stick such that every stick that comes later is no larger than the stick you are standing on. For instance, if you are standing on A2, this is the case. This is the case. Every stick that comes later is at the max the size of the stick you are standing on when you look to your right from A2. Okay. But if you are in A4, this is not the case. If you are standing on top of A4, your view is blocked by A5, A6, and by the way, not A7. By the way I've drawn it, A7 is slightly smaller. Okay. So if you are standing on top of a stick and look to your right, either there will be no stick that is larger than the stick you are standing on, or this is not the case. Now is the key fact. There are infinitely many sticks such that there is no stick to your right that is larger, or there are only finitely many such sticks. There are only finitely many such sticks. There are only two possibilities. Either that the collection of sticks which has the property that when you look to your right, no other stick is larger, this collection is finite or it's infinite. Okay. So please, this is the heart of the proof and this is that ingenious trick that I was talking about. Please pause the video and contemplate this for a few minutes to make sure that you understand that these are the only two possibilities entirely. Okay. Now we'll make the first possibility precise. Making the first possibility precise for infinitely many n in n such that if m greater than n, then am is less than or equal to an. Okay. There are infinitely many n such that if m is greater than, there are let me reword this to be grammatically precise. There are infinitely many natural numbers such that if m is greater than n, then am is less than or equal to an, not n, is less than or equal to an. Okay, this is the first possibility. Now I'm going to construct for you a decreasing subsequence of an using this possibility. How do I do that? Let n1 be the first natural number for which let me just label this star. Okay, for which star happens. It's the first natural number such that if m, let me label star correctly. Let's label this is what I'm going to call star. This is what I'm going to call star, not the whole statement. Let n1 be the first natural number for which star happens. That means if m is greater than n1, then am is less than or equal to an1. Okay, fine. So we have found the first term in the subsequence. Let n2 be the second such number. Okay, that means if m is greater than n2, then am is less than or equal to an2. Okay, we have assumed that there are infinitely many such numbers, so we can keep iterating this procedure and get a subsequence a and k. What is the special property of this subsequence? Well, if m is greater than nk, then am is less than or equal to ank. This is the specific feature of this subsequence. In other words, by construction, an1 is greater than or equal to an2 is greater than or equal to an3, and so on. That is how this sequence has been constructed. This shows ank is decreasing. Right. So in this scenario, in the scenario that there are infinitely many sticks such that when you look to your right, no stick is larger than the stick you are standing on, we have shown that there is a decreasing subsequence. The other possibility is that there are only finitely many such sticks. Only finitely many n in n such that if m is greater than n, then am is less than or equal to an. That means after a point, when you climb on top of a stick and look to your right, there will always be at least one stick that is larger than the stick you're standing on. No matter where you stand, after a particular point, there will be some finitely many sticks for which this is not true. Let's say till the sixth stick. You will not be able to find a larger stick to your right. But after a point, every stick that comes will have the property that when you look to your right, there will be some stick at least that is larger. And I am hoping that already you realize the proof. I'm going to leave it as an exercise because it's easy. Resolve this case. That is, find a strictly increasing subsequence of an. Okay. Now, you will be able to prove this quite easily. Once you are done with this proof, please sit down and think why the when there are infinitely many negative terms, We have assumed that there is a subsequence that consists of non-negative terms. Just think why, even if that is not true, that you have infinitely many negative terms, you can construct a similar argument. Okay, so this is an interesting lemma. Let's prove the Bolzano-Weierstrass theorem using this lemma theorem. This is the Bolzano-Weierstrass theorem. Any bounded sequence has a convergent subsequence. Proof. Immediate from previous lemma and the fact that bounded monotone sequences are convergent. That was something we proved in the last module, that any increasing bounded sequence is convergent. I left the decreasing case for you. You start with a sequence from the previous lemma. It either has an increasing subsequence or a decreasing subsequence. Apply the fact that any monotone sequence that is bounded is convergent to this particular subsequence, which is increasing or decreasing, and we are done. Okay. Now, because this result is so important and because the first proof is a bit tricky, we shall provide a more classical proof, which is a bit long, but nevertheless worth learning. Okay. Now, let an be a bounded sequence. This is the second proof. Okay. Be a bounded sequence. Let mod an be strictly less than m. M is some real number. We have fixed a real number, which is a bound. In other words, an is all in the set minus m comma plus m. That's what mod an is less than m means. Okay. So you have minus m plus m and all the terms of the sequence are in here. Okay. Now split this into two intervals right in the middle. Call this one J1, call this one J2. Okay. So split minus m into two halves J1 and J2. Closed intervals. Okay. Both J1 and J2 are closed intervals. So it's like this. I'm just splitting right in the middle. So here actually the midpoint will be 0 because it's symmetric about the origin. And consider these two sets. S1 is defined to be those natural numbers such that an is there in J1 and S2 is those natural numbers such that an is in J2. Okay. The key observation is that S1 union S2 is the whole of the natural numbers. Because S1 union S2 is the whole of the natural numbers, at least one of S1 or S2 has to be infinite. Okay. Say S1 for definiteness. It could be either, I'm just taking it to be S1 for for being definite. Now set I1 to be J1. Okay. So what have I done? There are terms of this sequence an that fall either in J1 or J2. I am looking at those indices for which an falls in J1 and those indices for which an falls in J2. For some, either for S1 or S2, in an should be in J1 or J2 infinitely often. Okay. Note, you must not make the mistake of thinking that there are infinitely many points in J1 such that an is, I mean, infinitely many points an are there in J1. That's not true. It could be the case that an's repeat. What is crucial is that the collection of indices for which an is in J1 is infinite. Okay, not the terms of the sequence. It could happen that the terms of the sequence are all the same. There's only one point in J1. That can also happen. It's just that there must be infinitely many indices. Now set I1 to be Jn and split. Now split I1 into two parts, which again I call J1 and J2 by abuse of notation. Call J1 and J2. Okay, I'm splitting I1 again into two parts. Okay, and just to not overburden the notation, I'm calling it J1 and J2 again. Now define these two sets S3 to be those indices in S1 such that an belongs to J1, and S4 to be those indices in S1 such that an belongs to J2. Now S1 was an infinite set and S3 union S4 is clearly S1. Again one of S3 or S4 must be infinite. It could be the case that both are also. And set I2 to be the corresponding J1 or J2. Okay. If S3 is infinite, set I2 to be J1. If S4 is infinite, set I2 to be J2. Okay. Now it must be clear what is needed to be done. In this way, repeating this in this way, by repeating, that is split into two intervals, look at those indices for which an is there in the first part and look at those indices for which an is there in the second part. One of these sets must be infinite. The either S5 and S6, one of them must be infinite, so on. When you repeat this argument, you will always get intervals, each of which has infinitely many indices such that an belongs to that interval. Okay, so in this way, by repeating, we get nested shrinking intervals Ij such that for each j there are infinitely many natural numbers with an in Ij. Okay, I'm just continuously splitting and choosing that subinterval which has infinitely many indices such that an is there in Ij. Okay, let A be the unique element in intersection over j Ij. There will be a unique element because this is nested shrinking intervals. At each stage, the length of the interval is being halved. Okay. Now, let n1 be just 1. Okay. Choose n2 such that first of all n2 is greater than n1, and second an2 is in I2. Okay, because I2 contains infinitely many terms an2, because I2 contains infinitely many terms of the sequence by our choice, this will always, you can always satisfy this. Having chosen n1 less than n2 ... less than nk, choose nk plus 1 such that number 1 nk plus 1 is greater than nk and a nk plus 1 is an element of I k plus 1. So you can see where this is going. We are trying to construct a subsequence such that the nth term is present in ik. Okay, that's the basic idea. The first term we don't really care, we are just setting n1 to be 1. For all the other terms, we are making sure that a and k is there in ik. Fine. Now we get a subsequence. Subsequence a and k in n this way. Okay. Now, as you can guess, this subsequence is not any old subsequence, it actually converges. How do you show that it converges? Well, fix epsilon greater than 0 and choose k epsilon such that 2m divided by 2 power k epsilon is less than epsilon. Okay, just choose k epsilon so large that 2m divided by 2 power k epsilon is less than epsilon. This can always be done. Okay, if small k is greater than k epsilon, then a n k is an element of ik by our choice, which is actually, we'll just call it akbk. Okay, and modulus of bk minus ak will have to be less than epsilon. Okay, note this follows because at each stage the interval ik is obtained from ik minus 1 by taking either the right half or the left half. That means bk minus ak at each stage is half the size of bk minus 1 minus ak minus 1. That is, ik is half the size of ik minus 1. We started off with 2m, size 2m, because we started off with minus mm, right? So it will follow that if you make the choice of k greater than k epsilon, with k epsilon being chosen such that 2m divided by 2 power k epsilon is less than epsilon, then it will follow that mod bk minus ak will be less than epsilon in size. Okay, and notice also that a is present in akbk. Okay, a is present in akbk. It is immediate that mod a and k minus a is also less than epsilon, because a is also falling in this interval akbk. Okay, so this shows a and k converges to a. So we have found the required subsequence a and k by subsequently partitioning the interval minus mm in such a manner that at each stage you are always left with an interval which contains infinitely many indices for which an is there in that interval, and from these intervals you are choosing one term in such a way to get a subsequence. And because these intervals are shrinking by 2 at every stage, it's becoming halved, it is easy to show that the intersection will have one point, and that point will be a limit of this constructed subsequence a and k. So this concludes the proof. This is the more classical proof, and this method is called the bisection method. The method that we have adopted here, it's called the bisection method. At each stage we are bisecting the intervals by 2. Okay, so the second proof is a bit long, but there are no tricks involved. It's a straightforward proof. It's just a bit technical. So please study this proof carefully. This is a course on real analysis, and you have just watched the module on the Bolzano-Weierstrass theorem.